Okay, so if you've seen my previous video about a simple TCP server with Paul, so while looking into this whole polling thing, I read a bit about Select, and I discovered also that there is this Epoll syscalls, which are basically an optimized version of Paul. And so I rewrote it in my little TCP server with Epoll, and then I made Claude write a little benchmark. And here are the results. And so we can see that, let's focus maybe on the throughput first. And we can see that, so the scale is the number of connections, the number of concurrent connection, and it's a logarithmic scale. So this is like 10,000. And we can see that Epoll is slowly climbing. So the throughput is up, and at some point it does slowly decrease. But the pole is just as soon as you hit what is it, like more than 1,000 connections, it's extremely slow. And also, like, there is two other tests here that benchmark run that timed out, so that took more than 30 seconds. And so this is just from the simple fact that if you remember the poll, you give it an array of file descriptors, and what poll will do is that it will just loop over all of these file descriptors, and then it will return, it will modify this array, and then also in your application you have to loop over this array, and you have to check, oh, is this one available? And so basically it's a linear complexity. The way Epoll works is that the whole data structure is inside of the kernel, and they have like a nice, you basically have a set of file descriptors of interest, which are kept in a red-black tree, apparently, which is just to have like a set of them. And as soon as one is available for reading, writing, or has any events on them, it will push that to a list. And then as soon as there is some elements in the list, it will return you only those elements. So from the kernel's point of view, it's like when there is an event, it's just constant time. And from your application's point of view, it's also constant time, since you just have to handle that one event. So yeah, let me just quickly show you maybe a more concrete example. So I've taken back, so yeah, I mean, this is why it's optimized and cool and so on. But now let's just take back our little TCP server application so that I can show you how you can actually use those Epoll. And I forgot to show, but on the graph you could see that the latency was about the same at the beginning, and then as soon as there is too many connections, I think the latency of Paul goes through the roof, while Epoll stays nice. So anyway, this is our previous TCP server. So I create a TCP socket, I bind it, I listen. There's a small modification which I made on both server, which is instead of listening to 8 connections at a time, we can listen to the maximum that the kernel can do, which improved Paul slightly, but obviously it's not enough. And so there's the code to accept a new client, and there is the code to do echo whenever the client sends something. So, oh, and I realized that I'm not zoomed in, so you probably can't see if you're on the phone. So let's zoom in, and so here first of all, you have to declare an Epoll, and so the Epoll, the whole data structure will be inside of the kernel, and the kernel will give you a file descriptor back, and that's what you will interact with. So let's have our EPFD, that's usually how they call it apparently, and it's going to be Epoll create 1 with 0 as the flags. We can assert that EPFD is different than -1, that's when there was an error. And so now we need to add the server file descriptor into this Epoll. So to do that, we will call Epoll control, like this, or CTL, with the Epoll file descriptor, the operation, which you can either add a file descriptor to the Epoll, you can modify the You can modify it, what events you're listening to, or you can remove it. And in our case, we want to add it, so it's Epoll ctl add, like so. We have to specify the file descriptor, that's the server file descriptor, and then we have to specify an event, and an Epoll event, which I will create here. Epoll events, we'll call it ctl event, because why not? And in this ctl event, you have to specify the events you want to listen to. So this is very similar to poll. You just say epoll in, and there is also epoll out, epoll air, and so on and so on. And then there is a data union, which I don't know, maybe I can just show it. So whenever Epoll will say that a file descriptor has a certain event, it will also return you the data that you passed when you added it to the Epoll. And so this is a union, and this can either be just a pointer of your choice, integers, or a file descriptor. And so in our case, let's just use the fd one. And so we just say data is equal to fd, and this is equal to server fd. That way, whenever we call wait later, we will get the server file descriptor, which is handy because we need it in the accept. Actually, I now see that for the server FD it's not needed, but for the client it will be needed. But let's just have it like that. So yeah, and now we can also check this return value because this is slightly cleaner. And now we need to have, similar to how in the beginning of the loop previously we called poll, now we will call epoll wait, like so. And this is quite similar to the thing. So this, you will pass it an array of events, which epoll wait will fill. In our case, to keep it simple, we will just have a one event because it's easier, like so. Events one. But yeah, you can have a small array of events, and that's easier if you have a lot of throughput to your thing. It's like it will better distribute the time between your application and the kernel instead of having to go back and forth a lot of times. So, and there is also a timeout, just like poll. Let's put it at 100 milliseconds. Let's have that here. Let's assert that res is different than -1, so that there is no error. Again, epoll, just like poll, returns the number of a file descriptor, the number of events which it has. So in our case, if it's 0, that means it timed out. So let's just ignore that. So now we can check if the event data fd is the server file descriptor. That means there was an event for the server, and that means that we need to accept a new client. So we do that. Here we accept the client, nothing new. And here, right after we accept it, we will add it to the epoll as well, like so. So instead of server fd, it's going to be client fd. And this will be client fd here, like so. And that's it. And else, so if it wasn't the server file descriptor, it has to be the client file descriptor. And how do we get the client fd? We just simply get it from the events that epoll wait generated. So it's data fd, like so. So we add it here, and then as soon as we can receive some data from it, epoll will generate an event and put the client file descriptor here. And that's it. So yeah, and when you close client file descriptor, it will also automatically remove it from the epoll data structure. So let's make this slightly larger, and gcc main. And so yeah, it does nothing, but let's have a little client, and let's say hello. and we can see that it works. Let's go in another terminal. Let's have another client, and we can type some stuff, and it works. And let's just have another client, and we can type some stuff, and it works everywhere. And our application is fully concurrent, and it's nice. And it also can detect when there's a client leaving. So yeah, that's most of it for Epoll. I recommend you check out maybe more in depth the individual man page of Epoll CTL, Epoll wait, Epoll create is very simple. But yeah, for example, I think what was it, Epoll CTL that I mentioned earlier. So you can, in addition to Epoll CTL add, you can modify basically the data or the events associated with this file descriptor, or you can delete one. So anyway, that's all for this video. I hope you enjoyed it. And if you want more videos like this where I break down maybe the performance of something versus something else, or some like more videos about Linux syscalls or syscalls in generals, just let me know and I'll do more, and I'll see you in the next one.